welcome to page 5 of our notes today, and this is where we're going to finish it up, where we're talking about the Wronskian. Suppose that each of the functions f of 1, f of 2, f of n of x possesses at least n minus 1 derivatives. Then the determinant of all of these functions is called the Wronskian. That's why we have a W right there. So it's the Wronskian of all those functions, and they possess f of n minus 1 functions. So how many functions that we have, we do one less. And that's going to make a square matrix, and we're able to find the determinant off of that square matrix. All right, it's called the Wronskian of the functions. So we have a theorem, the theorem in this scenario is called, so our theorem is if y sub 1 and y sub 2 all the way to y sub n be n solutions of the homogeneous linear nth order differential equation, then the set of solutions is linearly independent if and only if the Wronskian does not equal 0. So, another definition is that any set y sub 1 to y sub n of n linear independent solutions of the homogeneous linear nth order differential equation on interval I is said to be a fundamental set of solutions on the interval. So if our Wronskian does not equal 0, then we have a fundamental set of solutions. If y sub 1, y sub 2, y sub n is a fundamental set of solutions of the homogeneous linear nth order differential equation on an interval I, then the general solution on the interval is just the superposition of all of our solutions. So notice you have the c sub 1, y sub 1, c sub 2, y sub 2. So it's just that linear combination, or it's our superposition principle, where we just add all of our solutions together multiplied by the constant. All right, where c sub I, where I is 1 all the way to n, are arbitrary constants. So all of our c's are constants. So let's verify that the given functions form a fundamental set of solutions on the differential equation on the indicated interval, form the general solution. So what we're going to do is going to confirm that this is a fundamental set of solutions. So what we're going to do is we're going to just do the Wronskian. So the Wronskian of e to the x cosine 2x, e to the x sine of 2x. Set that equal to, all right, so now we're starting with our e to the x cosine 2x, and then e to the x, sine 2x. Let me go ahead and move this over because I'm going to have to take some derivatives of that. That's good. All right, so now let's take the derivative of e to the cosine 2x. It's going to be a product rule. So derivative of the first is this e to the x times cosine 2x. Derivative of cosine 2x is going to be minus 2 e to the x sine 2x. And then on the right, derivative of e to the x is e to the x sine of 2x. Derivative of sine 2x is going to be 2 cos plus, that's positive, plus 2 e to the x cosine 2x. And didn't have to write that down as much. Alright, so now let's go ahead and to the determinant, cross multiply. So we're going to go ahead and do e to the x sine 2x, and then we have e to the cosine 2x times e to the x sine 2x. So let's go ahead and multiply. So we're going to have e to the x cosine 2x times e to the x sine 2x plus 2 e to the x cosine 2x minus e to the x sine 2x times e to the x cosine 2x minus 2 e to the x sine 2x. Alright, let's go ahead and distribute. we're going to have e to the 2x sine 2x cosine 2x plus 2e to the 2x cosine squared 2x minus e to the 2x sine squared x cosine, that's sine 2x cosine 2x plus 2e to the 2x sine squared 2x. Go ahead and we're going to cancel out the e to the 2x sine 2x cosine 2x is going to cancel out. We're left with, I'll get rid of them, 2e to the 2x cosine squared 2x plus 2e to the 2x sine squared 2x. Pull out a 2e to the 2x, and we're left with cosine squared 2x plus sine squared 2x. That's equal e to the 2x times 1. So our Wronskian is equal to 2e to the 2x, which is not equal 0. So we do have a fundamental set of solutions. And so then our general solution is going to be y equals c sub 1 e to the x cosine 2x plus c sub 2 e to the x sine 2x.